Hello OT learners and welcome to today's OT physics series where we'll be learning linear expansion under thermal expansion or thermal expansivity. Now if you are new to the online tutor platform, kindly consider subscribing so that you do not miss any of our OT lessons from the online tutor platform. So without further ado, let's begin. Now, we want to start by looking at what the linear expansivity of a solid substance or a metal is. So, most solids tend to expand when heated and contract when cooled. So, assuming we have a metal or a solid of length, so we have a solid of initial length L1, which is at an initial temperature, let's say theta 1. Now, if we subject this metal of length L1 at temperature theta 1 to heat, there's going to be an increase in the length of the metal from L1 to L2 over a certain temperature range or increase, so from theta 1 to theta 2. Now, this expansion in the length of the metal from L1 to L2, the increase in length from L1 to L2 over a degree Kelvin rise is termed the coefficient of linear expansivity. So we call this the coefficient of linear expansivity. So what is coefficient of linear expansivity? Coefficient of linear expansivity, which is denoted by alpha, is just the increase in length of a metal. Coefficient of linear expansivity is the increase in length of a metal or a solid material when there is 1 Kelvin rise in the temperature of that metal. So mathematically, we represent the coefficient of linear expansivity alpha to be equal to the expansion in the length of the metal, that is L2 minus L1. So the increase in length or the expansion over the unit length multiplied by the change in temperature of the solid. So you can define coefficient of linear expansivity alpha as the increase in length per unit length of each Kelvin rise in temperature of that particular substance. So this means that we can express our coefficient of linear expansivity alpha to be equal to L2 minus L1 over L1 multiplied by the change in temperature here is going to be theta 2 minus theta 1. So this is our formula for linear expansivity. Now, other people can represent the change in the change in length or the expansion as E. So sometimes we can write the coefficient of linear expansivity alpha to be equal to E divided by the the initial length multiplied by the change in temperature of the metal. Now, the temperature that we want over here should be in Kelvin. Now let's look at this. When we have, let's say, 50 degrees Celsius and it has been increased to, let's say, 75 degrees Celsius. To convert this to Kelvin, we need to add 273 to this guy as well as 273 to this guy to get the result that we want in Kelvin. Now you realize that after adding 273 to both these units, if you subtract this answer, let's say K1 minus K2, the answer you will get will be the same as if you just subtract 75 from 50 over here. So because we are going to or because we are dealing with change in temperature, if you are given the temperature in degrees Celsius, you do not have to convert it to Kelvin before you use for your computation or your calculation, because in the end, whether you convert it or not, you are still going to get a change in temperature to be the same for your answer. But note that if you are asked to find the temperature, even if the unit is given in degrees Celsius, after your calculation, the unit of your temperature should be in Kelvin, because ideally you're supposed to convert it to Kelvin before you use for the calculation. But what I'm trying to say is that because we are doing subtraction over here, even if you convert them to Kelvin and you do the subtraction, it will be the same as if you maintain the temperatures in degrees Celsius and you still do the subtraction. But note that the temperature we are dealing with over here should be in Kelvin. Alright, now that we've clarified that, let's look at how to calculate the new length of the metal after the heat has been applied to the metal to cause an increase in the length of the metal. Okay, so we said that the coefficient of linear expansivity is equal to the extension, or E, per the unit length per the change in temperature of that particular metal. So if we make the extension or the increase in length the subject, we have E to be equal to alpha multiplied by the initial length multiplied by the change in temperature of the length of the metal. Now we know that from here, we know that change in theta is equal to theta 2 minus theta 1. So we have our extension to be equal to alpha L1, then into bracket theta 2 minus theta 1. The same way, we know that our extension is equal to the final length, or the final length of the metal subtracted from the initial length of the metal. So we have L2 minus L1 to be equal to alpha L1 into bracket theta 2 minus theta 1. Because we want to find the new length, which is L2 of the metal after the temperature has been increased from theta 1 to theta 2, we have to make L2 the subject over here. So making L2 the subject, we have L2 to be equal to alpha L1 theta 2 minus theta 1. Then we bring the L1 over the other side of the equal to sign. It becomes plus L1. From here, we can see that all of these guys are multiplying each other, and then we have L1 over here. Let's rearrange this. We have L2 to be equal to L1. Let's bring this guy first. Plus alpha L1 into bracket theta 2 minus theta 1. From here, I can confidently say my L2 is equal to, over here we have L1 common between these two parts of the equation, so we can factor L1 out. If we do that, we factor L1 out, we are going to have 1 left over here, as L1 multiplied by 1 will give us L1 back. Then plus, then over here we have alpha into bracket theta 2 minus theta 1. Then we close the bigger bracket. Let me use them as this. So from here we can see that if we expand this bracket, L1 multiplied by 1 will give us L1. L1 multiplied by alpha into bracket theta 2 minus theta 1 will give us alpha L1 theta 2 minus theta 1. So we can finally say, therefore, our new length after the temperature has been increased from theta 1 to theta 2 to cause the expansion of the metal is equal to L1 into bracket 1 plus alpha multiplied by theta 2 minus theta 1 bracket close. So this is how we find the new length of the metal after the metal has been subjected to heat to cause an increase in the length of the metal. Now let's have a look at some practical examples to further understand how to use this formula to answer some series of questions. So we want to look at the first example that we have. We are to calculate the expansion of 12 meters of a metal pipe when heated from 5 degrees Celsius to 60 degrees Celsius if the linear expansivity of the metal is 1.7 times 10 raised to the power 5 per Kelvin. Now we have to note that the linear expansivity, the unit is per Kelvin. That is something that we should take note of. So let's provide our solution over here. So we write down our solution. First of all, I recommend you write all the parameters that you have so that you know what you don't have and what you are going to find. So we've been given the initial length of the metal pipe to be 12 meters. So our L1 is 12 meters. And then we've been told that the metal has been heated from 5 degrees Celsius to 60 degrees Celsius. That means our theta 2 is 60 degrees Celsius. And then our theta 1, which is the initial temperature, is what? 5 degrees Celsius. We are to calculate the extension or the expansion, okay, if the linear expansivity alpha is equal to 1.7 times 10 raised to the power minus 5 per Kelvin. Now this is very simple. All we have to do is to find the extension or the expansion, which is E. So we do not know E, and that is what the question is asking us to find. So let's go ahead and look at that. We know that the linear expansivity of a metal or a solid substance alpha is equal to the extension per unit length multiplied by the change in temperature of that particular metal. Over here, we are supposed to make E the subject, as that is what we are going to find. So if we make E the subject over here, we cross multiply. We are going to have our extension to be equal to alpha multiplied by L1 multiplied by the change in temperature. So our E is going to be, our alpha is 1.7 times 10 raised to the power minus 5 multiplied by the initial length of the metal is 12 meters multiplied by the change in temperature over here is going to be theta 2, which is 60 degrees Celsius, minus 5, which is the theta 1 that we have over here. Now if we multiply everything we have over here, we are going to have our answer to be 0.01122, which means our extension or our expansion in the metal, okay, after the metal has been heated from 5 degrees Celsius to 60 degrees Celsius is 1.12 times 10 raised to the power minus 2 meters. This basically tells us that if we want to find the new length of the metal, L2 is going to be what? L1 plus the extension, as we know that extension is equal to L2 minus L1. So if we send L1 here, L2 is going to be L1 plus extension. So our new length is going to be, our L1 is 12 plus our extension is 0.01122. So our new length is going to be 12.01122 meters, as the length of the metal pipe after the temperature of the metal pipe has been increased from 5 degrees Celsius to 60 degrees Celsius. Now let's have a look at the second example under this topic. So example number 2, a wire 20 meters long is heated from a temperature of 5 degrees Celsius to 155 degrees Celsius. If the change in length is 0.020 meters, we are to calculate the linear expansivity of the wire. So let's look at the solution that we have for this problem. So we write down our solution. First of all, let's write down the parameters that we have. So we have a wire of length 20 meters. So we know our L1 is 20 meters. and it has been heated from 5 degrees Celsius, which is theta 1 is 5 degrees Celsius, and then theta 2 is 155 degrees Celsius. Now they are saying the change in length, which is L2 minus L1, which is equal to E, is equal to what? The change in length is 0.020 meters. And then we've been asked to calculate the linear expansivity of this particular wire. So all we have to do is to write down the formula for the linear expansivity of a metal. So we know alpha is equal to the extension or the change in length, which is L2 minus L1 over the unit length multiplied by the change in temperature. So our alpha is going to be the change in the length has been given to us to be 0.02 on the unit length is 20 multiplied by the change in temperature is going to be 155 minus 5. So this means we have our alpha to be equal to 0.02 on 20 multiplied by 150. So if we multiply this and we divide it by the top, we are going to have our alpha, which is our linear expansivity of the wire, to be 6.67 times 10 raised to the power negative 6. Now remember, because we have length over here, this is meters, this is meters, and the temperature over here is in Kelvin. So the meters cancels the meters. So we have Kelvin at the denominator, which when it comes to the top, it becomes per Kelvin. So the unit for our linear expansivity is per Kelvin. So which means for this particular wire of length 20 meters, the linear expansivity of that particular wire is 6.67 times 10 raised to the power negative 6. Now let's have a look at one final example. Example number 3. We have an iron rod of length 50 meters and a temperature of 60 degrees Celsius is heated to 70 degrees Celsius. We are to calculate its new length given that the linear expansivity of the iron is 1.2 times 10 raised to the power negative 5 per Kelvin. So let's write down our solution. So first of all, let's write down the parameters. We have an iron rod of length 50 meters, so our L1 is 50 meters, and then we've been told that the temperature rose from 60 to 70, so we know our theta 1 is 60 degrees Celsius and theta 2 is 70 degrees Celsius. We are to calculate its new length, so we are to calculate L2 given that our alpha or the linear expansivity of the ion is 1.2 times 10 raised to the power negative 5 per Kelvin. So let's go ahead and solve this basic example. Remember, during the introduction of this video, I made mention and we did some calculation where we got the final answer or the new length to be L2 is equal to L1 into bracket 1 plus alpha multiplied by the change in the temperature of the metal. So this is where this particular formula is much more applicable instead of going to all the hassle to derive it. So from here we know L2 is equal to our L1 is 50 meters, then into bracket 1 plus alpha is 1.2 times 10 raised to the power negative 5 multiplied by the change in temperature here will be the Q2, which is 70 degrees Celsius, minus Q1, which is 60 degrees Celsius over here. So we have our L2 to be equal to, this is 50 into bracket 1 plus 1.2 times 10 raised to the power negative 5 multiplied by 10. 70 minus 60 is 10. So our L2 is now 50 into bracket 1 plus 1.2 times 10 raised to the power negative 5 multiplied by 10 will give us 0.00012. So if we add these guys, we are going to have our L2 to be equal to 50 multiplied by 1.00012. So if we multiply these guys, we are going to get 50.006 as our final answer. So it means the new length of this iron rod after the temperature rose from 60 degrees Celsius to 70 degrees Celsius is 50.006 meters. So this is a basic introduction to linear expansivity under the topic thermal expansivity. So thank you so much for watching this OT phrases under thermal expansion, and then from here we are going to be dealing with volumetric expansion as well as superficial or area expansion. So if that is something you want to learn, thermal expansion will be, the link will be placed in the description of this video, so you can go click on that link and have access to the whole thermal expansion full tutorial. So thank you once again for watching, and I will see you in the next video. Bye bye.